this flow. Interfacial reaction is first. What does it mean? That if there is an interface, this side is beta, this side is alpha, as soon as one atom comes, it immediately jumps. So it is very fast. So, and beta and alpha then will be in their equilibrium concentration. So C beta will be somewhere up here because C beta is larger, and CE will be somewhere here. But immediately, instantaneously, the interfacial composition in the matrix side will reach CE because this is very fast. So there will be a concentration gradient that forms. Initially, this far away, it will be Ci, that is the initial composition of the alloy that is quenched to that temperature. So Ci. At certain other time, say Cp, and eventually it will be Ce. This is the process. So growth rate, if this interface moves at a rate of r dot, then r dot C beta multiplied by C beta minus Ce should be equal to number of atoms coming in the brackets. So r dot C beta minus r dot Ce should be equal to diffusivity and this del C del R at r equal to r. Say this distance variable I am writing as r. Why I am taking it as r? Because it is usually this is a spherical particle, then it is the radius. So at a particular point of time, say radius is capital R. Radius of the spherical particle is capital R. Although I wrote a planar, or I drew a planar thing, it is a spherical. So beta is this. Okay. So this radius is R. Understood? So at the interface, when R equal to, your origin starts from here. When R equal to capital R, at that time this del C del N, so concentration gradient multiplied by the diffusivity. So that is the number of atoms, that is the flux per unit area per unit time is coming. That should be equal to R dot C beta minus C. And whatever coming here, immediately those are jumping. So whatever coming at this point, immediately they are able to jump. Always we were writing this equation, that growth rate multiplied by the concentration difference equal to the number of atoms per unit area per unit time that is jumping. That should be that at interface, the interface flux. Interface flux, we are equating this with this. Now the question is how to find out del C del R at R equal to 1. That's what we will focus on now. Like this, that if there is a precipitant, it is an isolated precipitant in the infinite matrix, say one isolated precipitant. Okay, so some spherical cell you may think of, that these atoms are coming towards this. Okay, so at any point, number of atoms coming per unit time, at any distance, that should be equal. So that means BDR, or that means that At any distance, the area is 4 pi r square. 4 pi r square multiplied by d del C del R. D del, that is the number of atoms per unit time that is going inside. I am saying that is constant. That is constant meaning if you take derivative with respect to distance, that should be equal to 0 at any point. So that's the assumption we have taken. In that case, can we apply Fick's law? So if this is the case, this is constant. So ddr of 4 pi r square multiplied by d equal to 0. That means the inside is constant. So that inside is constant. That means r square del C del R is constant. Huh? Was CE. At the interface, your composition is CE. Huh? And somewhere here, say composition is C2. And they say this radius is R2. And this radius is say R. Then if I have this equation, I can write del C equal to constant del R over R square and integrate it. Integrate from R2 and CE to some concentration C. Is it okay? Right? Anyone please not following, let me know. This equation, del C is varying from CE to C2 equal to constant and del R over R square, and R is varying from R to R2. So we will get C2 minus CE equal to constant 1 by R minus 1 by R2. So constant is C2 minus CE over 1 by R minus 1 by R2. And we had R square del C del R. So this constant is nothing but R square del C del R. R square del C del R. Everyone is okay or fine? Right? R2. So I am taking a spherical cell in the matrix. This is your precipitate. In the matrix, I am taking arbitrary spherical cells of radius R2. And at the end of that R2, the concentration is C2. So I am saying that if you take any spherical cell, number of atoms per unit time that is diffusing inside towards the precipitate through a spherical cell area is constant, per unit time is constant. So area multiplied by the flux at that point is ddr of that equal to 0. That means inside this one is constant. So r square del C del R multiplied by 4 pi d, which is constant. So r square del C del R is constant. From there I could write this, and I integrated from whatever at the interface. So the precipitate radius is capital R. So capital R to R2, and at the surface of the precipitate